I feel like I've already talked about rectangular and doing the last three examples that we did. When you're computing, like I said, anything, you want to imagine that you've got these little packets of measurement and you're adding up the little packets of measurement. If you're trying to find volume, then you're trying to represent a volume. So I have a little picture here of a volume from the point of view of cylindrical coordinates. So it's basically a little box, but notice like the one side of the box is kind of curved. If you remember from trig class, arc length of a circle, okay, the arc length, not of a curve necessarily, but arc length of a circle is equal to, and the general idea is I've rotated some angle, okay, I've rotated some angle, and that angle is some fraction of the whole circle. If I'm working in radians, then what's an angle that makes a full circle? 2 pi, okay? So this is the fraction of the circle that I've traced, all right? And so that's the fraction of the circumference that I've traced. What's the formula for circumference related to radius? How do you find the circumference of a circle if you use
Pi r squared.
radius?
Pi r squared?
That's the area of a circle.
Area, sorry. 2 pi r.
2 pi r is the circumference of a circle. So notice the 2's and the pi's cancel. And so the arc length of a circle is given by the angle, if it's in radians, okay, I've written this out assuming we're working in radians. Because if I were not working in radians, what would be down here in the denominator? 360, okay? And so if you put an angle in degrees here, and you put 360 here, and then you multiply by the circumference of the circle, you're going to get the same number. But I have written it out assuming radians. So if I have the angle in radians, the arc length of a circle simplifies down to the angle I've rotated times the radius of the circle. So this side of my little packet of volume is an arc length. And so it's represented by r d theta, where d theta is the little bit of angle I've rotated. Okay, remember the whole idea about integrals is you have your measurement and you imagine making it smaller and smaller and smaller. So this curved side is an arc length. If I assume I'm working in radians, then it's r theta, but we're going to, instead of putting theta, we're going to represent it by d theta to emphasize that we're imagining this little tiny change in the angle to make my packet is smaller and smaller and smaller. This side of the box is change in radius. If I'm at this radius and then I go to this radius, this is the change in the radius, so it's represented by dr. And then this is change in height, so it's represented by dz. So length times width times height, if I multiply these three together, I will get a volume in cylindrical coordinates. Okay, so I'm still trying to represent volumes, so I need 3 dimensions. This is representing 1 dimension, a 2nd dimension, a 3rd dimension. So that's why when you're setting up a triple integral in cylindrical, it's not just dz dr d theta, it's r dz dr d theta, because r d theta is one side of the packet, and then dr is a 2nd side of the packet of volume, and dz is the 3rd side of the packet of volume. Okay, so if you're setting up a triple integral to calculate volume in cylindrical coordinates, you need to remember that one side of your box is represented by RD theta. And so there's gonna be an extra R in your integral setup. Does that all make sense? And so the pictures up here are just reminding us about cylindrical coordinates. This is the same information that was on, way back the first week of school when we were learning about, 3D systems. So it's just reminding you that to transfer between rectangular and cylindrical, x is equal to r cosine theta, y is equal to r sine theta, r squared is x squared plus y squared, and tangent of theta is y over x. All right, spherical has a similar discussion, so I want to talk through that before we start. Because what we're going to do then is we're going to have examples, and we're going to try to set it up using each of the three, and we'll kind of notice that for any problem, there's usually one best way to do it. Okay, so again, the idea is we're going to add up a bunch of packets of volume.